Hello, everyone. At the beginning, I have very bad news for you. For those of you who attended my previous talk, you could notice that I had some problems with my laptop, and it turned out that the problems are more serious than I expected, and I have to use another laptop, and I don't have a demo on that. So, unfortunately, sorry, no demo. Okay, briefly about me. I've been doing professional software development for nearly 15 years. I still am active developer, and I must say I love it. That's real aesthetical pleasure to look at elegant code, and that's what I'm doing on my daily basis, trying to figure out what makes good software good and bad software bad. My research background is in language semantics, compiler design, static analysis, and patterns and anti-patterns. Most recently, I founded Yonita, which is a startup focused on automated refactoring on various anti-patterns in software. So basically, various tricky cases in software are my daily job. Today I'm going to tell you about some performance and concurrency anti-patterns and the concept of Yonita Optimizer, which is a source-to-source translator. I'm going to show you 3 anti-patterns that refer to performance and concurrency, and I will show you how we can refactor them to achieve more efficient code. Also, I have very preliminary results of Hibernate core library refactored by Yonita Optimizer. This is Java. Yes, this is Java, my cat. I've named my cat Java. I sometimes joke that I've named her so because she's so fat. She might be fast, but by any means she's not slow. What about our Java? Is it slow? What do you think? Is Java slow? Yeah. In modern era, as you can see, on most intels, Java is faster than C. That's what William Moulin from European Space Agency Center said during JSON 2010 conference. It might be a pretty controversial statement. However, in the era of various new languages on JVM, yes, Java is comparing to them blazingly fast, right? So, where's the problem? Sorry, I have some problems with slides. It shouldn't be that order. Anyway, so if Java is so fast, why our Java applications are so slow? What do you think? I see that problem in the overall complexity of software, right? We use hundreds of libraries, and as you learned from my previous talks, it impacts not only security, but also performance. So huge technology stack is one of the worst problems of today's Java developers. When it comes to, because it's really tremendously difficult to manage those various libraries, to get to know them very well, that's why we have so many bad architectures, bad design, or simply inefficient code. So most of our problems, unfortunately, lies in our own code. Some problems might be connected with wrong configurations, like the wrong configuration of our application or database servers, OS, and so on. I remember the case when switching flag for caching in OS level changed completely the behavior of DB server, because DB server that time didn't have its caching switched on. So the problem is with performance that bottlenecks usually go unnoticed until happen, right? So we don't track our performance measurement. We do not measure the performance of our applications on daily basis. That's the problem of our quality assurance, right? I had a quick chat with Piotr Budzki, who gave a talk today or yesterday, and he was one of very few developers who told me about his approach to constant monitoring and testing on real data. That's very important. I'm sorry, that's not my laptop. My laptop crashed, unfortunately, for those of you who arrived late. So that's the problem with performance issues. Here we have this slide about the overall complexity of software infrastructure. Devo Boratz on Twitter, he said that today, hello world application in cloud involves one load balancer, 3 web servers, and 2 database servers. So true, so true. To build a very simple application, we use very, very complex infrastructure and hardware and software infrastructure. The study shows that the average application contains only 20% of custom code. The rest comes from other sources like open source libraries, closed source libraries, and so on. So we write only 20% of code which is actually executed on our machines. And how does our code look like? Usually it looks like spaghetti, right? And it's very difficult to track a single spaghetti line in such a mess. Sad reality. So I'm trying to see some patterns in that mess and to first automatically detect them and then to refactor them to a little better software. I really like this quote. Think, why think? We have computers to do that for us. And that's the concept. Yonita Optimizer is automated, fully automated. So it's like a compiler. It sort of reminds of a compiler because we translate one sources into the other. We try to refactor, with Yonita Optimizer, we try to refactor inefficient code structures into more efficient ones. At the moment, we support only a small subset of very generic performance AntiPatterns. We focus on a specific variant to get it working, just simply as that. Yonita Optimizer differs from a profiler. It's fully automated. It operates on sources instead of observing application during runtime. Also, we have a little bit different goals. Why? Because we do not try to spot the most the hardest bottlenecks. Instead, we optimize what we can, only what we are able to optimize. So with a profiler, we usually are looking for the hotspots, right? Here, Yonita does not necessarily provide you hotspot information. It only makes your code more efficient when it comes to some AntiPatterns. So now I'm gonna show you 3 AntiPatterns which we are able to refactor in very basic variants. That's not the full we do not cover all variants. Okay, what's this? Do you recognize this sequence? Exactly. That's the Fibonacci sequence. This is a very classic example of recursive programming, right? Because we do not have a simple recursion, we call recursive function twice. Fibonacci sequence and in Java, how does it look like? The most obvious implementation just follows the definition, so we have a simple recursive function. And where's the problem? The problem is that it has the execution time is exponential, right? So it grows, from some point it grows very, very fast. Why? Because the higher Fibonacci number we want to compute, the more redundant computations are performed. Because take a look at this simple tree. We start with 49, so we need to compute Fibonacci 48 and 47. And for 48, we need to compute 47 as well. So we see that for each level, we compute the same Fibonacci number twice as much as on the previous level. So it's simple exponential growth. So that's the problem we would like to solve. And our first, a very good illustration to our first anti-pattern, redundant work. So basically, redundant work is about executing unnecessarily the same block of code many times in a single execution path. Consequences are obvious. We have very slow performance. Please note that redundant work is not only about recursion, it's also about any other method, not only recursive method, which is performed many times. Probably it's heavy like database access. When we have many database accesses in the same execution paths to retrieve the same data, obviously we have a huge performance overhead. So refactored solution is to call this heavy method only once and store the computed result for further use. So it's the simple idea of caching. And Fibonacci refactored. I would love to show it working, but on the other hand, it would be like you get one source and you obtain the other source file. And the other source file looks sort of like this. So basically, we do not replace recursion, right? We just provide an additional cache instance to store computed partial values. And before we start the actual computation of Fibonacci value, we check in cache whether or not the value is already present in cache. Then we also change return statements. Before each return, we store the value in the cache for further use. And the solution turns out to be very efficient, right? Instead of exponential growth, we have like linear this time. Here it's a little bit distorted because of that exponential growth. So this is a simple technique which in algorithmic theory is called memoization. When you talk to any algorithmic guy about memoization, he would instantly think about caching, what we in enterprise development call caching. This idea is pretty well known. It's used in some other languages, like XSB Prolog, which is a deductive database. So Prolog is basically about programming by defining the problem, not defining the solution. Prolog to compute resolution, it uses the concept of SLD resolution, which is basically it's like searching of the possible solution and then checking whether or not they conform our definition of a problem. And XSB regular Prolog is very, very slow for some cases. XSB Prolog, which uses this kind of optimization, like caching of previously computed values, turns out much, much faster. I've learned it by my own mistakes and my own experience when I was using XSB and 6's Prolog a couple of years ago. As you could see yourself, we have a cache instance per each AntiPattern method. The keys in our cache map are arguments to the method. In our example, we had only a single argument, but we support many arguments. Then we create an artificial class just to wrap the arguments. And the values are obviously computed return values. And we just change two places in the code, the beginning and the return statements. It looks pretty simple, but behind the simplicity, we can encounter some problems. What problems? The problem is that our function, for example, for the first variant, when we refactor recursive functions with at least two recursive invocations, think about some dependency on random, on time, on some external resource. So we can't guarantee that the return value is the same for the same arguments, right? So the problem is when our function returns different values for the same input arguments. So we need to take into account this, and we need to check during our analysis whether or not it's sorry, whether or not it's valid. So it's sort of heuristic, during which we might be wrong. The second variant is even more difficult. At least two invocation in a straight single execution path. We need to take into account the modification of the state of the objects. Between invocations, we need to take into account side effects, as well as random temporal dependencies. In this case, we removed external source, like, for example, database dependencies, because in most cases, it's better to refactor, because those external sources usually are single managed by our application. They are not changed by the other external applications. But still, it's something we need to sort out, and we need to have a consistent approach to why doing such translations. Just to show you that redundant work, it's not only about such a classic example like Fibonacci. Here we have a simple excerpt from enterprise application which uses Java server faces. So we have a simple user bin which has a very simple get user method which retrieves user from the underlying database. And then we have a simple JSP file in which we display the fields of our user. What happens here? It was written by quite freshman developer, so to say. So she didn't know the details of how JSF works like, and she didn't realize that every time she tries to display something in JSP, get user is called. So we have many calls to database to retrieve the same data. Definitely, it's not our semantic and we do not allow the user. We do not expect user to be changed in this piece of code. So basically, this is a huge overhead because we have too many database calls, and also think that this was wrapped by like sort of application level services. So we also had some security management and so on. So every time we hit get user, we called also security authorization checks and so on. So imagine that we would like to display a simple user, and in the background we perform like hundreds of database calls. That's pretty inefficient, and that's a real world case. Okay. So that was the first anti-pattern. The second anti-pattern is about searching. This is pretty common code in our applications, right? That we have lists, and we iterate over the lists to find the elements which conforms to some conditions. This is pretty inefficient in case of large collections, right? Because we use like linear search instead, for example, of using more advanced data structures. Or not more advanced, sorted list is not an advanced data structure, sorry to say that. And unfortunately, such pieces of code are so common in enterprise applications. Why? I think because we do not conform to object-oriented principles in our enterprise development. We are more focused, the flow is more structural, right? So we don't have proper encapsulation. So we expose our collections. And when we are exposing our collections, users need to, of our piece of code, needs to iterate over them to find some elements that they need. So that's the root of this issue I see much deeper than on the surface, but that's another talk and another view on the way we write software today. Here we focus on anti-patterns and how to refactor them. So such one-by-one processing is time-consuming for large data sets, as well as also time consuming when we perform during that one by one processing some heavy operations, like for example database access, which is not that rare in the real world. So basically we need to, first of all, try to encapsulate and expose only interface useful for developers. That's one thing. And the other thing is that we should use smarter algorithms, data structures, like smarter. Still, I'm ashamed to call binary search smarter. Sorry. But binary search, sorted collections, maps with pre-computed search predicates are good solution to those kinds of problems. Our search refactored. Basically, this is a pretty difficult anti-pattern to get refactored because it has many variants. We need to treat each variant differently. For example, like finding a single element that conforms to given predicate, like finding greater than, lower than. We need to think about whether we return a single value, a list of values, and so on. We do not support at the moment assessment whether or not method is heavy and it hits database, for example. So we focus only on one variant, the variant I shown you before. So we introduce our own sorted list collection with generated comparator depending on the case. And then we just return a sublist for find greater than value. So this is like our injection of smarter algorithm in place of simple, not so smart code. And it works much better because in case of linear search, obviously the computational complexity is linear, and here we get like log n complexity. So in long term and for large collections, it's obviously much better. And the last anti-pattern, we have a piece of code which serves for password cracking, right? So this is a simple brute force algorithm. We have the list of passwords to checks. We launch 100 threads, and each thread performs such a piece of code that it basically retrieves first available password from the list, and then checks whether or not this password is equal to some hash code. So what's the problem here? Do you see the problem? We have synchronized very good because we share this passwords to check list among many threads. That's good. But our synchronized blocks is a little bit too long. Please note that check password is executed inside synchronized block. So we do not take any advantage of concurrent programming and multi-threading here. This is like a single-threaded model. So only one password at a time is being checked. Very simple mistake, but it introduces huge performance overhead. So it would be like linear search. Again, this is a little bit distorted, but still it should be very square, linear complexity. And we want to make it more feasible for modern computers. So the third anti-pattern is about long critical section. It's unnecessary code performed inside critical section, and the longer critical section is, the less performant our application is. So the solution is just to remove the codes outside the critical section. So yes, we see that we just move the piece of code outside the critical section. Here it looks very simple. It's not that difficult in practice, but we need to pay attention to some things. How to, for example, how to assess whether or not the code needs to be executed inside critical section or outside. Basically, it's that the object we synchronize on, if the block of code access it, we can't move it outside. So we need to identify pieces of code which do not touch our semaphore. And with password cracking refactored, we achieve much better times, execution times. It's still growing. It can't be other way, because the more passwords we need to crack, the more time we need to use. But we make use of multi-threading here. Instead of single-threaded model, which basically was the anti-pattern about, here we have more parallel execution. The first thing I would like to say, this is only a prototype, really very rough prototype. So we need to put much more work into it to make it working for real code. However, we managed to run it on Hibernate core. For those of you who saw me speaking at various conferences, you know that I'm a big fan of Hibernate. I've been speaking about Hibernate for like 2 years. I think this is a very good piece of software, but there is no piece of software which can't be better, right? So we always can be better, and Hibernate can be better also, especially that they use a lot of linear search constructs. So we try to run our optimizer with only one refactoring, because Hibernate code is pretty relatively large code base, at least for static analysis, it's large code base. It took 8 hours to refactor. I don't remember now. It's like 60,000. Required, unfortunately, manual assistance because our parser crashed several times. We use Recorder library, which serves as our front-end compiler. Unfortunately, the project is not supported anymore. The last release was a year ago. At least from what I found on the web page. So they don't have very frequent releases. But finally, we managed to get it working. What did we achieve? Not that much as I expected, but as I was telling you, that linear search refactoring is the most difficult ones from those we perform. It may produce pretty significant results, but we only support one simple variant at the moment. So we achieved some performance gains, but it was like 5 to 10%, so not that much. And there is nothing that comes for free. So with the performance gain we achieved, we lose like 20% of in-memory usage. So memory consumption obviously is bigger, but memory is cheap nowadays, right? So this is only very early prototype. It does not have any fancy interface, but if you want to give it a try, just email me. There are some problems with static analysis, with warranty of correctness. With static analysis, mostly they are like technical problems. I think that the concept is right. And we proved it on smaller examples, but to get it working on real code bases, we need to support reflection, which is always difficult for static analysis. We need to support different libraries and all those XML file configurations. And that's always pain in arse. So that's not easy, and it requires much more work. So for example, that case of JSP and Java server faces, we are not able to refactor it. Why? Because we do not support JSP. So if it was just plain Java, we could make it working. But with all those new fancy technologies, it's much more difficult to provide a complete solution. Warranty of correctness is also something, because some huge issue, because we need to, we use some heuristic. As you could see, if our function depends on some randomness, external sources, it's very difficult to analyze and to refactor. In such cases, we can just give up. There are enough bad constructs in large code bases to give some work to our optimizer. Also, thread safety is another issue, because we need to during some refactorings, thread-aware class becomes thread-unaware. So we need to keep that in mind as well. Also, we are considering achieving some hints from programmers, like using the annotations, like that can be a large collection. This might be a heavy method. It could help us in actual assessment, more correct assessment of what's the performance overhead and what's not. Because I think that even in case of linear search, is not a very bad practice for small collections, right? Even quicksort for small cases switches to linear search instead of some sort of linear sorting instead of quick sorting. So this is the future work. Feel free to email me. You can get access to this early prototype, but do not expect user-friendly interface. It's just pure console or interface. It would be great to achieve real-world feedback. Now I'm working on testing open source libraries and testing how much gain we can achieve with those simple refactorings. Thank you.